Say that again.
For
Sorry.
the contact details, we have to
Uh,
write our address, email
yes.
address.
Yeah. You have to write your postal address.
Okay, sir.
Yes.
Okay, sir.
Whatever you're comfortable. If you think that you
Okay,
can,
sir.
if anyone, if your school is
Okay, sir.
open, or if anyone in the school who can receive on your behalf, then you can give your school address as well.
Okay, sir.
Okay. All
Okay,
right.
sir.
Okay. Fine. So now, since I see people from 9 to 12 also, just asking, do you understand what is escape velocity? I mean, it is not
Yes,
for
sir.
whoever from not
So,
not from 4 to 8, but you know what is escape velocity, right? Or should I have to iterate from escape velocity? Not required, right? Or tell me if anybody needs that. Then I will explain. I don't know how to use the pen here though, honestly speaking. Let me open a couple of things like what is gravity and space velocity is what I can
uh,
show you now.
sir, you can use paint.
So escape velocity is just to give you a brief of it. It is say if you just to understand, like if you throw a stone from here to the sky, right? The stone will come back, right? If you can throw anything, it will come back. Now, if you can throw in a very high speed, at a very high velocity, then once the stone goes away, it will breach the Earth's gravitational pull, and it will no more come back. So that is what is known as the escape velocity. I will just quickly go through this one. The space velocity, like objects that travel around the planet, are called satellites. Right? Each complete journey a satellite makes around the planet is called an orbit. So, like Moon has an orbit, so does the man-made satellites are also have an orbit. Our Earth has one natural satellite, the Moon. However, since October 1957, many thousands of artificial human-made satellites have been placed in orbits around the Earth. To stay in orbit, a satellite has to travel at a very high velocity, which depends on the height. So typically for a circular orbit at a height of 300 kilometer above the Earth's surface, a speed of 7.8 kilometer per second, which is actually 28,000 kilometer per hour is needed. At this speed, the satellite will complete one orbit round and Earth in 90 minutes, right, around the Earth in 90 minutes. Satellites have to move so quickly in order to compensate for the pull of Earth's gravity. So this is another concept you will be aware of called the centrifugal and the centripetal force. So suppose you have a stone tied with a string and you just go on rotating the stone. You will see neither, since you are pulling the stone, right? So the stone should come towards you, and at the same time the stone is trying to go out because you are rotating at a high speed. So like the same, if you see this small satellite going around, so one force is making it to push it outside, and another force is trying to pull it inside. This is called centrifugal and the centripetal force that keeps the balance, and everything rotates. Everything or it orbits around the Earth's Earth's atmosphere or around the Earth, right? So that is where, because if you don't maintain this speed that it is going out and it is trying to going out, and then what will happen, it will slowly come down to the Earth's orbit, Earth's atmosphere, and slowly it will be sucked up by the Earth. So that's why it has to orbit in a particular high speed so that it will not come down to the Earth's surface. So that is why satellites have to move so quickly in order to compensate for the pull of Earth's gravity. This is similar to someone throwing a cricket ball or baseball. The harder the ball is thrown, the farther it will travel before it reaches the ground. So if a player could throw the ball hard enough so that it reaches the necessary velocity, the ball will go into orbit. It would never fall back to Earth. Throw it harder still so that it reaches a speed of 11.2 kilometer per second, that is 40,300 kilometer per hour, known as the escape velocity. and the ball will leave the Earth altogether. It will then become a satellite of the sun. So if you at one point, if you go out of the Earth's total gravitational pull, then that object will actually rotate along with the Earth. Then the sun's gravitational pull will actually pull it or make it not go away or roam around in the space because of the sun's gravitation. So am I clear for especially for students 9 to 12?
Yes, sir.
Right? Yeah, somebody has
Yes,
said.
sir.
Okay, good. So just to give a calculation, I'm not sure how can I do that. Maybe in the wave interface it is not possible to write in pen and paper. So eventually it is actually, I will write it. Wait a second. I can.
Yes, sir.
Wait a second. Let me see how can I write something so that you can be able to view the formula, but I think it's not possible. Maybe I will show some formula of the. It's better. I will show you something on that, right? So equation of gravitational or relation. Gravitational pull, force, I will say, with escape velocity. Okay. Now, I don't know why it's not showing the formula. So actually, this will give a better. Yes. Let me see.
Here's our last video on gravity. In this case, we're going to be talking about the escape velocity. In other words, when a rocket takes off from the Earth, how fast must it be going so that gravity will not slow down to the point where it will eventually stop and return back to Earth?
Not clear.
So, it doesn't have enough velocity, so even though it goes farther and farther away from the Earth and kinetic energy is being converted.
Say that again. Is video not clear?
Yes, sir.
Okay.
Sir, you hear me?
So it's clear.
Yes, sir, it is
I
clear.
think you do not.
Yes, sir, it is very clear.
Yes, sir, it is clear.
Sir, can you hear
Is
me?
it clear or should I
Sir,
go
no
continue?
problem.
So no problem.
Yes, sir, it's clear.
Okay.
Sir,
Okay.
continue. No problem.
kinetic energy to keep going and never stop. Or in the limit, when it finally reaches the infinite distance away from the Earth, at that point it can stop. At that point it will no longer fall back to the Earth because it's so far away from the Earth that gravity will no longer pull it back. So how do we find that escape velocity? The way you do that is using the energy equation, that the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. So since we're looking for the very minimum.
So you understand the potential energy and the kinetic energy, right? Half mv square and mgh. Are you aware of that? Guys, can you hear me?
Yes, sir.
Okay.
Yes,
You are aware of the potential and the kinetic energy, right? Okay. Fair.
Velocity required to escape, the escape velocity, we can say by the time it reaches an infinite distance, all the kinetic energy will have gone to zero. And of course, by definition, when your distance is at infinity, potential energy at that point is also equal to zero. So what we then have to say is that the kinetic energy initial plus the potential energy initial equals zero. Of course, the kinetic energy initial will have to be 1/2 mv squared. Of course, the velocity required is escape velocity, so we'll write v sub e. And the potential energy initial will be the potential energy it has at the Earth's surface. So it would be minus, I keep forgetting my g, so minus gm big M over r. That, of course, would be the radius of the Earth. And that has to equal zero. So now we're going to solve this equation for velocity escape.
So, guys, do you get why this is g, small n, capital N, and r e? That is Earth's radius. You got this one. This is half mv square is, this is the kinetic energy. This is clear. And I hope this you understand it. This is the kinetic energy. That half into the mass into the escape velocity square. That is the kinetic energy. And why this is capital G small m capital M divided by arc radius? Are you ever? Do you know why?
No, sir.
No, sir.
Even-
No, sir.
Even from 8 to 12, nobody knows why.
sir.
Okay. Okay. So this is the. Okay. Then I think. Okay. Hold on. Hold your thought for the time being. We'll come back to this G, small m, capital M by R E at a later stage. But as of now, just let's calculate what is the escape velocity as of now. Please go ahead. Please look into this, and then we'll come back to the G, small m, capital M, and the R thread.
So first
Sir,
of all, you
I
can see that
can't see or hear anything.
we have
Okay, so who is this? Can we talk after this meeting? I will explain you separately. Whoever is not able to hear or see anything, do let me know, right? Or do Bhaskar know, okay?
1/2 the escape velocity squared is equal to bringing this to the other side. It becomes positive. It's g m divided by the radius of the Earth. Then we multiply both sides by 2, so we get v initial squared is equal to 2 times g m over the radius of the Earth. And finally, when we take the square root of both sides, we can see that v, and it should not be v sub naught, it should be v sub e, because we're looking for the escape velocity. So we see that escape velocity is equal to the square root of 2gm over the radius of the Earth. All right, now I noticed something here. Let me rewrite this and maybe you see it as well. So if I now take the escape velocity is equal, this pen is indeed better. I'll write as the square root of 2 times the square root of gm over the radius of the Earth. Notice this quantity right here. What does it remind you of? That is actually the orbital velocity equation. So we can say that the escape velocity is equal to the square root of 2 times the orbital velocity of the Earth. And so that can now simply be an equation like that, where the escape velocity.
So yeah, I think whoever has got it, it's fine. Whoever not, maybe we can have it. We can discuss separately on that. So this is there is a formula for the escape velocity with respect to the Earth's gravitational pull, right? And it is a simple equation is that you have to calculate the kinetic energy and the potential energy, and the kinetic energy is nothing but half m, that is the mass of the m is anything. It can be you also, it can be the rocket or anything which is the target you are going to send out of Earth's orbit, out of Earth's surface or to the orbit of the Earth, right? That's small m, and it will have a velocity ve, that is escape velocity, and then that should be equal to the mgh. Mgh stands for the mass of the same target that we are going to send out, g for the acceleration due to gravity, and h is the radius where you want to send, so the height. Now whenever you make that equation, you will derive that it is actually the Earth's gravitational pull is like the g is the capital G is a constant, right? That is the 6.7 into 10 to the power 11, and you have the Earth's gravitational pull is 9.8 meter per second square. I mean, the acceleration due to gravity is 9.8 meter per second square. That you can find it out, and you can easily find out what the escape velocity is. So whenever we need to send a rocket, we have to ensure that the rocket is given such a velocity that it reaches the escape velocity and gets out of the Earth's orbit, Earth's surface, and goes into the Earth's orbit and can rotate into the Earth's orbit. Okay. So any doubt so far? I am sorry because I cannot explain in pen and paper, or I mean whiteboard. I don't have a whiteboard, and maybe I need to ask Bhaskar how can I do a whiteboard session in the Google Meet. Then it will be quite helpful for you to explain in a kind of thing. But if you have any questions, do let me know. Yeah.
No,
All right, ready to go for the next one. So now I will talk about something called the Death Star death.
Sir, can you hear me?
Right, not going into the black hole right now. First, I will talk about the star death because I
Sir,
talking about
sir, can you?
the black hole and the star. So First of all, do you know how a star, how the star gets energy? How the sun gets energy? So sun continuously gives us energy, right? The solar energy or whatever, the light energy, the heat energy, the sound energy even. So there's a lot of energy. So there is a lot of combustion or other lot of reactions are going on inside the sun. What kind of reaction is that? Are you guys aware of that? If anybody knows, can you just put? Yeah, what is that?
Sir, sun has helium, which is converted into
And
hydrogen, which is used for burning. But
Okay. No, it is the
sir,
other
it
way.
has,
It's the other way. So you know, all of you know that nuclear bomb, right? There is, we know the tragic incident
yes,
of the
yes,
Hiroshima
sir.
and the
yes,
Nagasaki that
sir.
happened. That's
Yes, sir.
the atom bomb we know as. So atom bomb works something called the nuclear fission. Fission means an uranium particle will be broken down into, sorry, I forgot, into two elements. I think one is, when uranium breaks down, what it breaks into? When uranium breaks, it breaks into what? Okay, so it breaks into two elements. I'll let you know of seeing the periodic table, and that is where, and it generates huge energy, and the energy is nothing but equivalent to E is equal to mass of that particular particle of the atom, like neutron or what proton it has, into m, that is a mass, m into c square. C square is the velocity of the light squared, right? So that much of energy is released by that. On the other hand, there is something called nuclear fusion. So fusion means two protons basically combined together into a single nucleus, two proton into single element. Like two hydrogen will combine together to create a helium particle or a helium atom. Two hydrogen atom will combine together to create an helium atom, and there also lot of energy will be produced because of the formula, like E is equal to mc square. So mass into the velocity of light square. So when all the hydrogen atoms inside the sun gets converted into helium, it has no more hydrogen atom to be converted into helium. So then all the helium atoms will start combining together, and they will create some kind of carbon. Then they will create some kind of, they will create carbon, oxygen, or iron. And as a whole, the all the sun will actually run out of energy, and that cause the death of the star. Right? Most that is what I'm let here. If you see this is thing, most stars. Hello, anybody, any questions? If not, okay. So most stars take millions of years to die. When a star like the sun has burned all
So
of
am
it,
I audible, sir?
yeah, yes,
Oh, okay. Now it's working. Okay, sorry. Sir, actually,
hello,
the you were saying that uranium breaks into.
yeah, yeah.
Sir, it breaks into three neutrons and krypton and beryllium.
Krypton and beryllium, right? Okay, yeah.
Yes, sir.
So, okay, good, good. Yeah. So, even since you are at which class you are? What is your name, sir?
12, 12.
12. Okay. What is your name?
Shorik Poddar.
Sorry. Okay. Sorry. Yeah. Sorry, I cannot see. Okay. Sorry. Oh, sorry. Yes. Good. Yeah. So sorry. Yeah. Just thanks for this one. Yeah. So yeah, this current, that's if krypton and beryllium it breaks into, and after that it produces a lot of energy. But I'm just coming to the question how the fusion happens, like two hydrogen proton combines into helium, and the thing there. So when a star like the sun has burned all of its hydrogen fuel, it expands to become a red giant. This will be millions of kilometers across, big enough to swallow the planets Mercury and Venus. Right? After puffing off its outer layers, the star collapses to form a very dense white dwarf. One teaspoon of material from a white dwarf would weigh up to 100 tons. Over billions of years, that white dwarf cools and becomes invisible. Stars heavier than 8 times the mass of the sun end their lives very suddenly. When they ran out of fuel, they swell into red supergiants. They try to keep life alive by burning different fuels, but this only works for a few million years. Then they blow themselves apart in a huge supernova explosion. If you don't know about supernova explosion, maybe we'll talk later. But as of now, imagine that there's a huge explosion happening, creating lot of light and energy, which gives birth to the other stars basically. So for a week or so, the supernova outshines all the other stars in its galaxy. It's a really, I mean, it outshines everything, outshines all the other stars. Then it quickly fades, and that is left in a tiny dense object, a neutron star or a black hole, surrounded by an expanding cloud of very hot gas. The elements made inside the supergiant, such as oxygen, carbon, and iron, are scattered through space. The stardust eventually makes other stars and planets. So, a black hole is created because of, I mean, it's obvious, you can understand that since hydrogen has a single proton, right? And its atomic mass is definitely less than that of a atomic mass of carbon. So when you take the same, if you guys are aware of the mole, right? The molecular weight, right? So the same amount of mole will create heavier mass in terms of carbon than if I take the same number of molecules, right? Than number of hydrogen. So that becomes a very dense object. That's a thing, which weigh 1 teaspoon of material will weigh 1,000 tons. Now, when the mass goes high and your surface of the planet or surface of the star goes reduces, then what will happen? The gravitational pull is actually, if you remember, the gravitational pull says is nothing but the constant g, which is 6.7 into 10 to the power 11 mass of the, say the big M is the mass of the star divided by the r square. Then r becomes very small. So what happens? And the mass becomes high. So eventually you end up in such an object which has very high gravitational pull. Now that gravitational pull is such high that just now we described the escape velocity, right? Such high that the escape velocity is greater than the speed of light. So now when the escape velocity is greater than the velocity of light, what will happen? The light will enter, but it will not come out because it will be sucked into the black hole. That is the reason why a black hole is created. I mean, it's created because of a Death Star. Now, what is the difference between the black hole and a neutron star? So the neutron stars are generally smaller in size because it is full of neutrons, but it is not as a black hole because its mass is still less to make the escape velocity higher than higher than the speed of light or the velocity of light. So am I clear? Shaurik, if you have any questions, and folks, anybody can have any question, please unmute your microphone and ask me.
So can you say about that again, that neutral star?
Oh, okay. Neutron star. So as I mentioned, right, neutron star is a little bit smaller in size compared to the black hole because of a smaller radius. I mean, because of radius, and since the neutron star has the mass will be it's equivalent to the same. I mean, the mass or the mass will be same, but or the mass will be less, I will say, so that the gravitational pull is not as high that the escape velocity is greater than the light of velocity of light. So it does not absorb all the light. It is actually very massive star you can think of, but not to the extent that the gravitational pull is such a high that it is more than the escape velocity of light. Clear, sorry? Who asked the question?
So, one last confusion I'm having is, so the neutron star is the like, it's not a black hole, right? So it's the previous one of the black hole.
It will not become black hole. The reason is that it has to attract enough mass inside it and it has to go dense into it to become a black hole. So you can think of black hole is a more of a powerful engine or the difference between a drone versus helicopter.
Okay, sir.
right? So both have the same principle, if you see, right? But a helicopter can carry people, and it can even carry a battle tank as well along with it. But a drone cannot. Drone cannot even it will be heavier for a drone to lift a small camera as well, right? So that's the thing. So the neutron star is in a smaller black hole, but it is a dead star. You can think black hole and neutron star both are dead star. But black hole has become such a massive because of gravitational pull that it takes light inside it. So maybe we'll come to the black hole now quickly.
Sir, what is the difference between a red giant and red supergiant?
Repeat the question again. Sorry, who asked the question?
Sir, I.
Okay.
Sir,
So
what is the difference between a red giant and red supergiant?
red giant and red supergiant.
Yes, sir.
Okay. This is also, I don't know. I have to look into it. Something will be there. Maybe it is based on the size of the star. That could be. So I will get your answers. Sovik, which class you are in, Sovik?
Sir, 7. I am Aishman. That's my father's name.
Oh, okay. What is your name?
Aishman.
Ayushman. Okay. Okay. I'll come to you. The giant and the super giant, right? Yeah. Okay. So now coming to the black hole, what it is, the black hole is all about, right? So black hole are the strangest object in the universe. A black hole does not have a surface like a planet or star. Instead, it is a region of space where matter has collapsed in on itself. The catastrophic collapse results in a huge amount of mass being concentrated in incredible small area. I mentioned, right? So when it becomes too dense, the surface area reduces, the radius, the gm by r square, the r reduces like anything, and the m grows like anything. So it becomes literally infinite, if you can see. If I reduce the r and I increase the capital M, then definitely it will be very dense, concentrated of high gravitational pull. The catastrophic collapse results in a huge amount of mass being concentrated in an incredible small area. The gravitational pull of this region is so great that nothing can escape, not even light. I mean, the reason why you cannot escape, because the escape velocity is more than the velocity of light. Right. Another thing is that black holes cannot be seen. We know they exist from the way they affect nearby dust, stars, and galaxies. Many of them are surrounded by disks of material. As the disks swirl around them in like a whirlpool, they become extremely hot and give off X-rays. So with the help of that only, we can understand there is a black hole. Black holes come in many different sizes. Many of them are only a few times more massive than the sun. These stellar mass black holes form when a heavyweight star about 10 times heavier than the sun ends its life in a supernova explosion. What is left of the star, still several solar masses, collapse into an area only a few kilometers across. Most galaxies, including the Milky Way, have supermassive black holes at their centers. These may be millions or billions of times heavier than other sun. Supermassive black holes also power active galaxies and ancient galaxies known as quasars. Quasars may be hundreds of times brighter than even the largest ordinary galaxies. Objects that fall into black holes are literally stretched into to breaking point. I don't know whether I'm saying in the last call or not. Like, so if you jump into a black hole, you will not, like, for example, you jump here from thing, you just land, right? But there, the shape of your body will change. An astronaut who ventured too close was sucked into a black hole that will be pulled apart by the overpowering gravity. So what will happen? Even if you put a pencil, what will happen? The pencil will get elongated. Now, why the pencil will get elongated? Because the tip of the pencil will be pulled with more gravitational pull than than the tail of the pencil. So similarly, if a human being, if he jumps into the black hole, his head will be pulled, so his body will get elongated. because his head will be pulled much faster than his legs.